In the last lecture, we started discussing PN junction diodes, and we also looked at one of the applications of these diodes in the form of a full wave rectifier, both without and with a capacitive filter. So today let's look at a couple of other applications of diodes. The first kind of circuit that we are looking at is a clipper circuit, and in particular we are going to look at what is called a parallel clipper circuit. So let's say we have an AC input, so this is what the circuit looks like, and we are going to measure the output across these two terminals. So I'm going to put a load resistance over here. So we have a diode D and a resistance. During let's put the input signal over here, Vin, which is sinusoidal. Now during the positive half cycle, this diode will conduct, and the potential across the diode is just the barrier potential. So the output is just the barrier potential and nothing else. So where this is VB. During the negative half cycle, the diode is in reverse bias. So there is no current passing through the diode. All of the current will flow through the load resistance. So in this case, you get the full output as the input is. Once again, during the positive half cycle, the current will flow through the diode because it's in forward bias. So you get an output like this, and then reverse bias. In the negative half cycle, it's reverse biased. So again, this way. So as you can see, we have managed to clip the input signal during its positive half cycles. So this is called a clipper circuit. What if I didn't want it clipped at VB, but if I wanted it clipped at some other value? Well, that's pretty straightforward as well. Then all I need to do is, in series with this diode, I'm going to put some DC voltage. Let's call it VK. Now, instead of during the positive half cycle, instead of being clipped at VB, it will be clipped at VB plus VK. And what if I want it to be clipped during both positive and negative half cycles? Well, that can be achieved as well. What if we do something like this? Maybe I should put a resistance here. So now during both positive and negative half cycles, it will experience clipping. And now my output will look like this. So that's a clipper circuit for you. There are also other applications like clamper circuits, etc. And one can look at those in the book. Now, if you remember, when we were talking about diode characteristics, so V versus I passing through the diode. In the forward bias, it looks like this. In the reverse bias, this is what it looks like. And this is called the breakdown voltage. Now what one can do is one can construct a special kind of diode which is meant for using in this breakdown or avalanche region. If you take a normal diode and you try to use, if you increase the reverse bias voltage too much, so if you start from here and keep going this way, you will eventually damage the diode. But you can create a special kind of diode known as the Zener diode, which is meant for using in this breakdown region. And that is achieved by changing the amount of doping. Depending on how much doping you put in your diode, the value of the current at which the breakdown occurs will change. It can go all the way from a few volts to hundreds of volts. So this breakdown voltage is also called the Zener voltage, VZ. Now, what is the point of using a diode in this avalanche or breakdown region? Well, if you look at the voltage versus current characteristics, you find that, first of all, you'll see that the resistance is very low because there is a large change in the voltage with a very small change in current. So you get very high conductivity. That's one thing. Other thing is, this acts like a very efficient voltage regulator, which again comes from the fact that delta V over delta I is large. Sorry, yeah. Not large. It is 1 over this, which is large. So delta V over delta I is small. Essentially what this means is that you can keep changing the current, but the voltage will remain almost fixed. So this can be used as a voltage regulator. So for instance, suppose I'm sending in an input voltage over here, and now I want to put a Zener diode over here. So the symbol for a Zener diode is like this. It's similar to that for a diode. That's a Zener, and it obviously it is always operated in the in reverse bias. So let's say this is the input over here, and I'm going to measure the output over here, and you can see that the output across this Zener against this reverse biased Zener diode will always be the Zener voltage. So this acts as a voltage regulator. There are lots of other special kinds of diodes also that one can talk about. We will not discuss them in this course, but you can read more about them in the literature. For instance, you have light emitting diodes, or what we call LEDs. There are photodiodes whose output will depend on the amount of light shining on it. Then there are special devices called varactors. There are Schottky diodes, etc. Look them up. They have very useful applications. LEDs, of course, you are familiar with. Possibly also photodiodes you may have heard about. So the next thing that we want to discuss is transistors. You can think of a transistor as being made from two diodes together. So for example, if you have an NP diode and a PN diode, then you can think of them forming an NPN transistor, or you can have a PN with an NP giving you a PNP transistor. These were invented in around 1950 by Bardeen, Brattain, and Shockley. And well, these have three parts which are referred to as the emitter, the base, and the collector. I believe you have also studied transistors very briefly in your 12th standard. So, of course, now because you have two interfaces, you have two barrier regions with potentials over here. Typically, the doping of these three parts, the emitter, the base of the collector, is such that the emitter has maximum doping, followed by the collector, and the least doped is the base. Now, in a transistor, typically you have the current is being carried by both the majority current carriers or the minority current carriers. So hence they are known as bipolar junction transistors or BJTs. Later in the course, we will also look at some unipolar junction transistors or UJTs, which will have some different properties. In a circuit, what is the symbol that we use for transistors? It looks like this. So if you have a PNP transistor, this is collector, base, emitter, and you have an arrow pointing inwards. If you have an NPN transistor, then the symbol is looking something like this. Collector, base, emitter with the arrow pointing out. So you always put the arrow on the base emitter leg of the symbol, and the arrow points, you can think of it along the positive conventional current direction. So from P to N always. Okay. How does a transistor work? Now the emitter, because it is highly doped, has a large number of majority current carriers. So we want a current to flow, we want these majority charge carriers to flow from the emitter to the base. So the base emitter junction is always forward biased, but if you look at the collector base junction, here you want the minority carriers from the base to flow into the collector. So this junction must always be reverse biased. This is also something that you have seen in some detail in your 12th standard. So for instance, if we have an NPN transistor, let's draw what it might look like. Emitter, base, collector, and this is N, this is P, this is N. Then the base emitter junction must always be forward biased. Let's call this VEE. Whereas the base collector junction must always be reverse biased. This is, yeah. So typically, this is the kind of biasing that we do. In the base emitter part, we have the current flowing, no, the other way. because we're talking about the conventional current flow. So this current is known as the emitter current. In the base collector junction, you have what is known as the collector current. And finally, at the base also, because of recombination of majority and minority current carrier, electron and hole recombination, you have a small current IB flowing in. So IE equals IB plus IC. This is simply the total current being conserved. Now usually IB is much less than IC. Therefore, IE and IC are almost the same. I'll define a couple of quantities over here. The first is what is called alpha, which is defined as IC over IE. Or you can think of this as IE minus IB over IE. Now, because IB is much smaller than IE, this quantity you can see is almost 1 but slightly smaller. And I can also define beta, which is IE over IB and this is typically large because IB is much smaller than IE. And beta is a value that is typical for each transistor. So when you get a transistor, it will come with some specific beta value specified for it. Beta can change with temperature, for instance, but if you're operating it constantly at normal temperature, then you have a fixed value of beta. There's a specific name for beta. Beta is called the current gain. Now, typically, let's say you have some circuit with a transistor. And you are going to send it some input and you are going to collect some output. So you need a total of 4 terminals, 2 for the input, 2 for the output. But your transistor, of course, has only 3 legs: collector, base, and emitter. What this means is that one of these 3 is going to be common to both the input and to the output. So correspondingly, there are 3 possible modes of operating a transistor. A transistor can be operated in common base mode or configuration, common base, or in common collector mode, or in common emitter mode. What would a typical circuit look like? Suppose I'm talking about the common base mode. Then my circuit might look something like this. This is base, collector, emitter. I'm talking about NPN transistors. So my input comes across these two and my output comes across these two. As you can see, the input is between the collector and the base, whereas the output is between the emitter and the base. So this is common base mode. What does a common collector mode look like? Base, emitter, collector, NPN. So now the input is between base and collector, and the output is between emitter and collector. So this is the common collector mode. And if you want the common emitter mode, base, collector, emitter, NPN. Input between base and emitter, output between collector and emitter. So this is your common emitter mode.